In this lesson, we're going to be talking about relays and contactors. Now, the relay is an electrical device that consists of a coil and a set of contacts. The coil and the contacts are isolated, thus protected from each other. It's designed to be usable where one circuit must control another. The schematic symbols of a relay are a bunch of symbols put together. You'll always have a coil, you'll have normally open contacts, and you'll have normally closed contacts. You only have one coil, but you can have numerous sets of contacts within that relay. The coil is a spool of wire wrapped around an iron core. The coil is energized and a magnetic field is generated. This field pulls in an armature that opens or closes a set of contacts. When a relay is shown in a schematic, it is always shown in the de-energized mode or position. Every coil has a voltage rating. This rating is the voltage that you may apply to the coil. These ratings are normally 24 volts, but can be 120 volts, 208, 230. The coil will not work if the wrong voltage is applied. In fact, in some cases, if you have like a 24 volt coil and you apply 120 or 208 volts to that coil, the coil will actually melt down and you can get smoke and flame. The coil rating is normally stamped on the side of the relay. The coil is considered a load in the schematic circuit, so you do not want to put the coil in series with another load. The contacts of a relay are a switching device. Normally refers to the position of the contacts when the coil is de-energized. Relay contacts come in two varieties. You might have a normally open and you might have a normally closed. Relay contacts are attached to the armature that is moved by the magnetic force of the coil. The relay contacts have metal points that come in contact with each other. These points complete the electrical circuit. Relay contacts will be labeled on a schematic to correspond to the coil that controls them. For example, the fan relay could be labeled IFR for indoor fan relay. The contacts could be labeled IFR1, IFR2, IFR3. So when you're looking at a schematic to find what controls what, look for the labeling on the relays and the contacts. The normally open contacts are shown on a schematic diagram as a set of open contacts. When the relay coil is energized, the normally open contacts close, allowing electricity to flow through them. When the relay coil is de-energized, then those contacts will flip back to open. The normally closed contacts are shown on a schematic diagram as a closed set of contacts. When the relay coil is energized, the contacts open, not allowing electricity to flow through them. When the coil is de-energized, those contacts will close back to their normal position. Now, contacts are also rated. They're rated with the number of amps that they can control. The contacts are rated with the type of load they can control. This would be either an inductive load, like a motor, or a resistive load, like a heater. Remember the words inductive and resistive. Inductive loads, their amperage will change when they're energized. Resistive loads, the amperage remains stable when it's energized. With inductive loads, the amperage spikes when it is starting and then levels out. With resistive loads, the amperage remains as a constant. Make sure the contact ratings exceed the number of amps that the load is rated for. You don't want to use a 10 amp motor on a 5 amp rating. So when you look at motor amperages, you have a few different types of amperages that might be stamped on the motor nameplate. You have a running load amp, which is called RLA. It's similar to a full load amperage, FLA. It's the amperage drawn by the motor when operating at its normal operating condition. You also have a locked rotor amperage. This is the amperage drawn by the motor at startup. The locked rotor amperage is 5 to 7 times greater than the RLA or FLA. Both the LRA and RLA must be considered when choosing a control device. When you're looking at relays, it's important to realize that the coil and the contacts are completely isolated electrically. The only connection is magnetic and mechanically. The technician can de-energize and remove the wires from the relay contacts for the purpose of ohming them out even if the coil is energized to operate the contacts either open or closed. This is a good way to determine whether or not a relay is working properly. An example of this would be the relay coil is energized with 24 volts. The technician has removed the line voltage and isolated the contacts and is reading 0 ohms across the normally closed contact and infinite ohms across the normally open. He determines that the contacts are not switching positions. Maybe the coil is broken or the contacts are stuck. Either way, you're going to replace the relay. This is an example of a relay circuit. In this case, the coil 1, C1, is not energized. Notice SW1 is open. Your normally closed contacts are energizing the lower bulb or load. The normally open contacts have prevented the upper load from becoming energized. Now, we close switch 1, we energize the coil C1, and we flip the position of those contacts. Your normally open C1 is now closed. Your normally closed C1 is now open, so the energized load swaps. And then when you open it back up, it goes back to its normal position. Now, the most often relay you're going to see is considered the Mars relay. Now, Mars is a brand name. Since then, numerous other people have duplicated this relay, but it's still known as the Mars relay. It consists of a coil and 2 sets of isolated contact. Each set has a common, a normally open, and a normally closed connector. Your normally open is on one side, normally closed, and a common. The coil is down at the bottom, 2 terminals on the bottom. One's a common and one's your power feed. So you can have three different circuits, or can have, on one relay, and they're all completely isolated. So if you take a look at the schematic of the relay, pins 1 and 4 is a power feed to the equivalent 2, 3, 5, and 6 contact positions. And then you have your coil, which is off to its own. Contactors work on the same principle as the relay, except they're larger in size. The contacts are able to handle more amperages. The contact points most often are visible, and the larger ones can be rebuilt. They're usually definite purpose, normally open contacts, and they're used to energize larger motors. The contact coils are rated by voltage. The contactor contacts are rated by amperage. The ratings are normally just as relays written on the side of the contactor. Do not install a contactor into a system that goes over either of these ratings. Your contactor has to exceed the ratings of all the motor and components that are connected to it. This is 2 examples of a contactor. Okay, the one on the left is a single pole contactor. Okay, what it does is you have contacts over, you have terminal connections over here on the left on each side. That's a constant. That's always energized. The one on the right, you see, has the armature and the movable points on it. This one breaks based on the relay coil or the contactor coil being energized or de-energized. The one on the right here is a heavier commercial type contactor. Okay, it has made mainly for a 3-phase circuit, has 3 sets of contacts. They're either all open or closed based on the coil being energized or de-energized. You can see the label right down here for the coil. Okay, it's a 120 volt coil in this case. Your load for the contact side, your ratings are over here on the right on the label. It also says up top, it's a 30 amp contactor. So you do not want to exceed 30 amps on this. The contactors are built, and the components in the contactor is the housing, a coil, a set of stationary contacts, the movable contacts or armature, and then just some separators to make sure the wires don't come together. Okay, and then you have your coil connections. The way they're wired into a circuit is you have your coil, which could be line or control voltage. Most often, in the case of air conditioning, it's control voltage. You have your L1 and L2 connections. Then you have your connections to your compressor and motor. Contactor out of the box would look like this. Again, you have your L1, L2. You have your T1 and T2, which is to your loads. And then you have your two coil connections. One's common, and the other's coming usually from Y on the thermostat. And if you stick in the schematic diagram symbols for this, you have normally open contacts and a coil. Or you can display it this way. Now, there's one thing it's very important to check when you're maintaining contactors and when you're looking at them for preventative maintenance. You see two sets of terminals here, okay? The one that's shiny and bright new is the way it is out of the box, okay? It's not pitted, it's not burnt, and you get a good even electrical connection when the two parts come together. The one that's looking pitted and burnt is after a couple years of use. It's very important to check and make sure that the points are not pitted, especially on heavy commercial equipment. If the points become pitted and burnt like this that you see here, it's time to replace the contactor. So again, in this presentation, we talked about contactors and relays. The importance is the voltage on the contactor relay coil, whether or not it's, and then the amperages and voltages rated on the contactor and relay contacts. Relays and contactors can have one voltage controlling it and another voltage on the load side. The purpose of them is to be able to use low voltage, low current systems to control extremely high voltage, high current devices.